Now let's talk about the DFS tree in the DFS simulation. So in this algorithm, we have not discussed this line in algorithm 6. We did not discuss add edge VW to T in our simulation. So let's see how it works out. First, we will have to do a DFS simulation, and in this DFS simulation we will keep track of couple of things. One, parent node. Parent node is a node that is used to discover the new node. Next, we will keep track of discovery time. Discovery time is the time when a node is first visited. Then finish time. The finish time is the time when all of the adjacent node of any node is visited. So if our starting node is D, there is no parent node of D, so we don't have anything here. D is visited or discovered at time 0, so we have 0 here. Next, we will discover an adjacent node of D, which is C. Even if there are some other adjacent node, for example E and F, we will always discover the node in an alphabetical order. So C is discovered via D and discovered at time 1. There are no other nodes that are adjacent to C, so we can finish processing for that node C. So we will keep track of finish time for C as 2. Then we will go back to D and discover another adjacent node if there are any. So we see there is another node adjacent to D in alphabetical order, E. E is discovered via D and at time C. Then we will go through E. From E we will discover G at time 4. From G we will discover H at time 5. From H we will discover A at time 6, and from A we will discover B at time 7. From B we can see there are no other nodes we can discover. There are no adjacent node from B, so we can finish processing all the adjacent node of B at time 8. Then we will go back to A. There are no other nodes that are adjacent to A, so we will finish processing A at time 9. Similarly, H at time 10, G at time 11, E at time 12. Then we will go back to D. D has one more unvisited adjacent node, which is F. That means F is discovered via D at time 13. There are no unvisited adjacent node of F, so we can finish processing F at time 14. We will go back to D. Finally, we will finish processing D at time 15. So this is a table you will have to fill up in the exam. This table will be different for different starting node. So for this graph and the starting node D, this is the table, and this table is generated using the rule that we always visit an adjacent node from a list of nodes alphabetically. When you do DFS simulation, you will use some of the edges to discover some new nodes. So here, if you look at the graph, we have some red edges which will be added to the DFS tree. There are some edges that are black which are not added to the tree. For the DFS simulation, all the edges of the graph can be divided into some classification. First, tree edges. The node that helped us to discover an unvisited vertex are called tree edges. Here, tree edges are DC, DE, EG, GH, HA, AB and DF. Next, forward edges. Forward edge connect an ancestor of a tree node to one of its descendant node. So if you take a look at the example here, HB, we already said that these red edges form a tree. So if you take a look at the node H and B, in the tree that formed by red edges, H is an ancestor of B, and the edge HB connecting an ancestor H to its descendant B. So the HB, this edge is called a forward edge. Similarly, if an edge connect a descendant to its ancestor, that edge is called backward edge. For example, in this graph, GD is a backward edge. Important fact about the backward edge is this type of edge signifies that there is a cycle in the graph. If you take a look at the cycle D, E, G, D, because we found a backward edge, we can say there is a cycle. The last type of edge is cross edge. Any other edge that are not the tree edge or forward edge or backward edge is called a cross edge. In this example, one of the cross edge is FC.